In today's lecture, we will talk about functions, since functions are the bread and butter of functional programming. And having an understanding of the properties of functions is quite important in order to grasp the subject. I will apologize to any mathematicians listening in, since I will probably brutalize this subject. But I'm a chemist, so I don't care. Functions. What is a function? And if we want to be a little bit formal about it, we can actually go to set theory and look in set theory. And for anybody who hasn't read any set theory, I really recommend going to the fundamentals and reading some set theory. It's the fundamental language of modern mathematics, and it's really enjoyable to read if you are into like stretching your brain a little bit and think about abstraction in general. I can recommend a book on set theory for anybody who wants to read up on the subject. It's quite readable, even for non-mathematicians. It's by a guy, his name is Charles Pinter. The book is published by Dover, which means that it's very cheap. It costs about, I think it cost about $10, and the book is called A Book on Set Theory. And it's a really nice exposition on the subject for laymen, and also I think probably for mathematicians. So that's just a little side. Anyway, so if we go to set theory and ask the question, what is a function? We can do something like, we can define a triple, right? Bear with me. A, B, F. So we have three things. A is a set, B is a set, and F is a rule to pick elements from A and B and form pairs. And that rule can either be true or false. So what is a set? Well, if you're not a mathematician, a set is just a collection of things, whatever. It can be empty, it can contain elements like integers or floats or Legos or whatever you might want to put into your set. It can contain other sets and so on. So sets are very general. It's just a collection of stuff. If you're a programmer, well, it's basically well, it's not a dictionary. Well, it's like a dictionary, but you can only have unique things in it. That's a set. So we've got two sets and we've got a rule. And now we can look at, so what is this rule? How does that rule work? So the way it works is we can write a table. So we can say, here's set A, and now I can pick out an element, call it x1. It's just some randomly chosen element from A. And then I can pick some random element from B, which I could call y1 in this case, or yx or yx1, whatever. And then I can take my rule f and I can say f given x and y, is that true or false? And f will say, oh, that's false. So then I have to delete that from my table. And I can go through over all the elements of B and check, and hopefully there should be one element for which this is true. Let's call that one y1. So I can take an x2 and I can repeat the procedure and I get the y2. Until I have done all my x's and gotten all my y's. Yes? So that's basically it. So this is what we can say, well, this is f applied on some element, or applied on A, or we pick elements from A, we test it, and we pick elements from B and we test it with the rule f, and this is what we get. And that's basically it. So the first thing we can note is that I chose the letter F because because that's the f for a function, right? So now we're getting close to something that we can say is a function. And the first thing we can note about functions is that a function is just a table. It's a table. Given a value, it will give you another value. Given another value, you get a new value. So it's just a mapping of values to other values. Super simple thing. Functions are incredibly simple, really. Now, I haven't really said much about the rule f yet, and we'll get to there. But this is the first result we have. Functions are tables of data. Now, of course, A and B might be both infinite sets. So this table will get very, very big. And of course, then we can also conclude that there's an infinite number of functions. So if we want to tabulate all the functions in the world, then it's going to be one big table or a big set of tables. But in principle, with our mathematician brain, we can, because we don't care about storage. These are just big tables of data. And this is interesting because now we say, okay, functions are the same thing as data. So there's no difference. There is no difference between functions and data, which is quite interesting. And we will use that fact a lot when we do functional programming. All right, so let's have a little look at little bit of a look at the rule f. So one of the first rules of f, there are two important rules for f. Only two. Maybe if you're a mathematician there are more, but there are two really important rules that we need to consider. One is that f has to pick and be able to pick every element in A. So there cannot be stuff in A for which f is always false. Right? There must be a line, there must be an element, so given that particular element in A, there must be some element of B such that this is true. Otherwise, it's not a function. That's rule number one. The other rule that we have is that given an element of X, element of A, there can only be one unique element of B. So that means that for any given value, any given element in A, there can only be one value in B for which this maps. That means that that mapping has to be unique. So let me draw some pictures to make this clearer. Let's draw A, and let's draw B, and put some elements in them. This is the beauty of set theory. We don't really care what these things are. But these need not be the same size. There can be a lot fewer elements in B than there is in A. So if I draw arrows here, let's say that this element here maps to that element, and that element maps to that element, and that element maps to that element, and that element maps to that element. This is an invalid situation because there is an element which doesn't get mapped anywhere. Of course, since this is a set, this is fairly easy to remedy this situation and turn this into a function by simply kicking out that element, and we're done. So that's not really a big problem in practice. If we have any elements for which this is not valid, kick them out, and we're good to go. But as you can see, I draw this picture so that, let's put this arrow in here, so that there are two different elements of A mapping into the same element of B. And that's perfectly fine. That's perfectly fine. That's no problem. And there can even be elements in B that we never reach. That's also fine. It's no problem. But what is not fine is if I would draw another arrow here. This is no. That you cannot do. Because now I have a single element in A getting mapped to different things in B. And then the rule must necessarily be false. That, on the other hand, that doesn't mean that this is some crazy construct, that this is invalid in some other way of looking at things. On the contrary, this is a perfectly valid thing to do, but then it's not a function. Then it's called a relation. And relations are also very useful to programmers, but not so useful to functional programmers. If you remember from an earlier lecture, I talked about relational programming. That's where these guys come in. So if you're a Prolog programmer, this is your bread and butter. Yes? Then you can have these multi-valued functions or relations, where you ask a question about something and you will get multiple answers back. Yes? This is a little bit like friendship. Huh? I'm a single element in the set of human beings, amongst human beings, but I can have many friends. If I were to be a function or map a function on me, I could only have one. And that would hopefully be my wife. Yes? But then there's a problem when you get kids, and then it gets very complicated. Then you have to go and become a Prolog programmer instead. So, yes, so that was a little bit about the functions. So, some nomenclature. This is not important really for being a functional programmer, but if you read literature, these things crop up every now and then. So in a function, the starting A here, the starting set, that is called the domain of a function, and this is called the co-domain. Yes. So that's just some names on things. We like to name things because then it's easier to remember them. All right. So let's do a little example here, because a really trivial sort of about functions is if we can do a constant function. This is really the simplest function we can do. So we have a bunch of stuff here in A, and we have a B which contains a single element. Right? So this means that all arrows point into the same poor little element in B. So if we would write this, we could say f of x, just using normal high school math syntax, f of x equals some constant c. Let's call it 42. So whatever you give it, it will just give you back the value of 42, and of course we can graph that thing. So here's the y value and here's the x value, and we can give it whatever x and it will just give us 42. For now and to eternity. And nothing will change it. Now if you're doing non-functional programming and you're using procedures, you can't really be sure about this. Your constant function might suddenly just decide that, ooh, yeah. You can't trust it. But if we know that it's a function, then we know what we have, and that's good for understanding things. So that was just an example of a sort of the simplest function we really can do. All right. So before we continue this journey, let's just have a quick little look on a couple of special cases of functions. So the first special case that we can have from the completely general case is that suppose we have some elements in A and B, And now I can say, okay, if I have the situation where every element in A is mapping to a unique element in B. Not necessarily all elements in B, but there is a one-to-one correspondence between elements in A and B. For every A, there is a single B, which means that we don't have sorry. Yeah, now I should draw another picture, but we don't have two arrows coming to the same into the same element in B. So there's only one arrow to every B. These functions have a name. They are called injective. And this will not be in the exam, by the way, so don't worry. So this is injective. If you speak Latin, if you speak Greek, it's called monomorphic. Maps to one. So this is one case. Then we have another case, special case, which is well, we can have it like this. Right? Just an example. So now we have the situation where this is not injective, since there are many arrows going to one element, but we cover every single element in B. We always cover every element in A, but now we also cover every single element in B. In this case, we only happen to have two elements in B. So if we cover the whole codomain, then this is called, if you speak Latin again, surjective. Or if you speak Greek, epic. Or if you speak English, onto. All of these terms are used. This function is onto B, which means that it's just covering everything. Oh. Right. And the third special case is the combination of these two. And that's the whole reason why we are talking about these things, because that one is really important. And that's when I have a one-to-one injective and surjective mapping. So let's put some 3 dots in both, and that goes there, and that goes there, and that one goes there. So this is both injective and surjective, and that's called bijective. And what makes this special and especially interesting to us is the fact that if you look at it, it can go both ways. It's a function both ways. It's a function from A to B. It's also a function from B to A. So it's what we say invertible. And you can say that it's going this way, it's called f, and going this way, it's called f minus 1. The inverse function. And if we look at something which is injective, we can see that, okay, so that looks fine, except that there's an extra element in B, which prevents us from inverting this function, because there is no, you can't have this dangling element in our domain. So if it's just injective, we can't really invert it, because there will always be some element that we can't touch. And if we look at the surjective case, then you will see that for this particular element here, it would have 3 different values, and that's absolutely a no-go for a function. But in this case, every single element is uniquely mapped back and forth, and we can go both ways. And this is very closely related to something I already mentioned, which is isomorphism. Now, if you're a mathematician, you're gonna, oh, it must be monotonic and it must be this and that and so on. We don't care. Isomorphism is closely related to bijective functions. There are also other definitions in category theory and where have you, whatnot, but But this is one way of looking at an isomorphism. And now we see what it really means. It means that, you know, we can take something and we can map it over to something else, and then we can just say, oh, and map it back. If we know these two, we have an isomorphism and we're happy. And those are useful, as you will see very shortly. Okay. So now we're sort of in the position where we can get to the really meaty stuff, the stuff that we're going to need when we are programming. So let's go back to our really the beginning here. We said we had a triple. We had a set A, which is our domain, and then we had a codomain, which was some set of elements. What if this element is a function in itself? So what would this be? This would be a rule connecting elements in A to functions of this type G in this set here. This is a set of functions. That would be pretty interesting. So if we simplify our syntax a little bit, I'll just write it up here. I hope you can see it. So in the first case we had A, B, and F. And this we can write, we already saw that this was basically what we could say F is X equals Y, using sort of high school syntax. Another way of writing this is F is a mapping from A to B. So if we do that in the same spirit here, let's say, okay, so in this case, what do we have? We have F here is a mapping from A to, and then we have this other mapping, G, which is a mapping from B to C. This is a function which takes an A and gives us a function back. And the question is, how is this useful? Well, let's look. So first of all, one of the first things we can do is we can actually rewrite this, because this is just a label. So what we really have here is something which maps an A into a B, which maps it into a C. Right? So what would this mean? Okay, so now suppose I have an A. I can give it into my first mapping. It will spit out the function. And suppose now I have an element of B. I can give it back to B, which is the function I got back. So first I produce a function, and then I apply that function again, and I get the C. Right? So actually we can remove these parentheses here, and I can write it like this. In a slightly simplified manner. And I should say that this syntax here is actually not the randomly chosen one. We will see this syntax a lot when we are programming F#. Because what we really have here, and what we have invented now, is a function of two variables. A function of two variables is nothing but a function returning a value. You need to think about that for a little while, but that's really what happens. So, yeah, that's how it works. We'll do some examples of this very shortly. Now, interestingly, we can rewrite this. Or we could actually write this function, just for the sake of it. Let's do it. Let's say f of x is a function which returns 5 plus y squared. Right? So what is this? oh, sorry, we should start 5x, for example, so that we use the x, otherwise it would be kind of pointless, right? So f of x is a function which returns 5x plus y squared. Okay? So suppose now I give the value of 1 to f of 1. Well, what would that give me? That would give me 5 plus y squared, which I can name h of y. And now I can say h of 2, and that would be 5 plus 2 squared, which is 4, which is equals 9, which is our result, right? Is that clear? Which is the same thing as actually as writing, I could have written fx comma y equals 5x plus y squared, and we could give this one, the guy 1 and 2, and we will get the same result. And now we just showed something quite interesting. We can look at this like this, or we could look at it like this, where this is a function returning a function, and here it's a function of a pair. This is a tuple or a pair, right? And they both give the same result. And you can actually show quite easily that this exact same thing here can be written as A, B. This is the mathematical way of saying pair. It's a star, gives a C. And that these two things are isomorphisms. Isomorphic. So there is actually no difference between a function of a pair of values and a function returning a function returning the value. They are exactly the same. And they all reduce to table lookup on table lookup on table lookup in the end. And in fact, this is such an important result that we have a name for it. So this form here is called the curried form. And this here is called uncurried. And they have received these names from the American logician Haskell Curry, who has also given the name to the programming language of Haskell. And so what we can say is, if we have a function in this form, so given a pair, we can curry it, and it will go into this form. And how do we do that? Well, that's going to be an exercise for you. It's very simple. You just write the function to curry it. And we can do the other way around. We can have a function in this form and we can uncurry it. So which one should we prefer? Does it matter? Why is this important? Well, one of the cool things that we can do in functional programming, which is kind of sort of weird for non-functional programmers, is that we tend to prefer this form, because we can do something called partial application, which is exactly what I did here when I said f of x. We had this function and I put in a 1 and applied that, and I could give it a name. And what happens then when I partially apply something, so look, I had 5x, and then I put in the x and I evaluate that, and well, in this case I just got 5, but if we would do f of 2, I would get 10. And now our original 2, which we had here, has been stored inside this definition of this new function in something called a closure. Again, an important word to remember, because that's used a lot, closure. It has been enclosed into this thing. So we carry it with us. And this is clever because now what we can do is when we are programming stuff, we can build functions gradually. So we just call them with a single argument, although they take 5 or 6. We call them at high up in our program with a value, and then it gets passed down in a closure, and we add more and more and more until we get to the final place where the whole thing is evaluated when we have collected all the stuff we need. Boom, we have a result, and we send it back up to be output to the user. So this is useful. This gives us a lot of flexibility. Partial application. Functional programmers love it. All right. So that was partial application. So, there's one case we haven't looked at. Actually, there are many cases we haven't looked at. You can easily cover them in your head, but there's one that we need to think about. So, let's go back to the triple again. What if my domain is not a simple set, but is a set of functions? Well, we could call this G here, whatever, we'll call this F. Right, so we have this situation. Now the set that we're starting with is a function. And then we got some values, or who knows, these could be functions as well, actually, if we want to make things really complicated. So what is going on here? Well, let's have a look. Let's write this in a slightly simpler form. The first thing we have is G from A to B. This produces a C. And this is our mapping F. And of course we know this is just a label, so we can just write it like this. But now we can't delete the parentheses here, because otherwise we will do the wrong thing. We will end up with what we did in the previous one, which is just a multivariate function, because this is something different. So now the problem we have at hand is that, okay, how do I call this thing? How do if you look at it, this is weird, because somehow I need to give this value into this function so that it can produce me another value so that I can do this mapping. And how is this going to work? What is this thing? Well, we can write it down. So let's suppose I write a simple function of x, g of x. And we can say, well, this is x plus 1, just for me to do something really simple, right? So this is a function which takes a value and produces a new value. Plain and simple. So it matches this scheme here. All right, so let's write an f. And let's say that it takes something called g. Like, these names are, of course, whatever. I could call this whatever. It doesn't matter. But let's just call it g. And say, well, this g here is, this function here is plus 1. This is my function definition. Okay? So now I can take my g here, I can pass it into f, and that would result in, replace this with this. And remember, since we have referential transparency, since we don't have any global variables and we don't have any I/O going on, anything, this is perfectly fine. I can just replace g with its definition inside of this whole thing here. And then g is x plus 1 plus 1. And now I know that, oh, I called it with 5 inside my f definition. So I can replace that with 5. And we get 5 plus 1 plus 1. And that should give us 7. Hooray! But the cool thing is that I can call f with a load of different g functions. I can just say, well, g could be of x, could be, call it g prime, could be x squared. And now I can call f of g prime instead, and then I would get 25 plus 1, which would give us 26. So these are useful. And they turn out that these are probably much more useful even than partial application, which is sort of a convenience thing, more like because there's an isomorphism there that you can between using the curried and uncurried form. But this is something quite unique. And this is what we call Hoff. And that's not from David Hasselhoff. These are higher order functions. And they turn out to be amazing tools for abstraction and for reuse. And we will see these all over the place, all the time, and in due time, you're going to love them. I do admit that before you get used to these things, both using partial application and in particular higher order functions, is a little bit mind-bending. It takes a little bit of training to get used to them. And once your brain will accept them, they will become your best friends. So that was basically all I had for this lecture. In the next lecture, we will talk about lambda functions. And lambda functions are just normal functions. But they are like dogs that we can teach new tricks. And it's actually the lambda function which is sort of the fundamental basis of all functional programming. And when we look at lambda functions, we're going to be using these tricks that we went through today in a lot, all the time, all over the place. So until then.